This is called a half Atwood machine. So an Atwood machine has two weights hanging over pulleys and they can move up and down. Here I have one weight over a pulley and one on a table. And this is a modified Atwood machine. I should write that up here, right? I should write Atwood. Named after Atwood McAtwoodson. That's not true, I made that up. This is a modified half Atwood because there's friction on this block right here. Now, we have a constraint, right? And the constraint, we have two things that we know. One, if this block, since these are attached by a string, if this block moves down some amount, that block has to move over the same amount. So the horizontal acceleration of this block has to be equal to the vertical acceleration of that block in the negative direction. They have to, otherwise the string would get longer or shorter. Also, the tension in the string acting on this box has to be the tension on the string on that box. So I know those two things. So let's just go ahead and draw a free body diagram for mass 2. It would look like this. I have the weight m2g, and then I have the tension. And I put the tension as slightly less, right? They're not equal. If they were equal, the box would be at rest. And we're assuming the whole thing's going to accelerate like this. So that means that the tension would have to be less than that in order to make the acceleration down. Let's go ahead and write Newton's second law for this one in the y direction. F net y is going to be equal to t minus m2g, and that's going to be equal to minus m2a. So it's minus because I'm assuming the acceleration is down. I could be wrong, but I'm assuming it's down. Okay, that's why it's that way. Now let's draw the force diagram for this one. It's a little bit more complicated. So for this one I have the tension pulling to the right. I have the weight, m1g, different weight, and then I have the normal force pushing up, and then I have friction, let's call it F, friction that way. In this case, I'm going to assume it accelerates that way, so let's call this the x direction and this the y direction. Now, if I want to find the friction force, I'm going to need the normal force. So if I want the normal force, I'm going to have to write Newton's second law in the y direction for this block. So F net y is going to be equal to n minus mg. That's m1g, right? And because the acceleration in the y direction would be 0 because the block stays on the table. So those are the only two forces in the y direction. They have to add up to 0. But I can use that to solve for n, and I get n equals m1g. The magnitude equals that. Now I can go over in the x direction. F net x is going to be equal to the tension minus the friction force. And this is going to be equal to m1a. So I'm assuming it accelerates in the positive x direction. So this is a positive number, but it has mass m right there. For the friction, I can say the friction force is equal to the coefficient times the normal force. But the normal force is m1g. So if I put that in down here, I get t minus mu k times n, which is m1g. And that's equal to m1a. Okay, so there's an equation. There's an equation. And so I don't know t, I know m2, I know g, I know the negative sign, -1, I know m2, I don't know a. So this has two variables I don't know. I don't know t, I know mu, I know m1, I know g, I know m1, I don't know a. So also has two unknowns. So I have two equations, two unknowns, I just need to solve that. So let's keep those equations right there. Now, how can we do this? What we want to do is to pick one of the equations, solve for a variable, substitute in the other one. So I'm going to take this and solve for t. If I add m2g to both sides, I get t equals m2g minus m2a. And I could factor out the m, but I'm not going to. Now I can substitute that in down here. Instead of t, I'm going to write that. So this equation becomes m2g minus m2a, that's my t, minus mu k times m1g equals m1a. Now I only have one variable. I know that, no. I don't know a, I do know, no, don't know. So let's get all of our knowns and unknowns on one side. I'm going to add m2a to both sides. I get m2g minus mu k m1g equals m2a plus m1a. And I'm going to go ahead and factor out the a. So I get m2 plus m1a. And I barely squeezed that in before it went off the screen. That's a thumbs up for me. How long does it take to do a thumbs up? Okay. A little bit longer. I'd like to go a little bit quicker on that. Okay, now I can divide both sides by that m1 plus m2, and I get a equals all of this. m2g minus mu k m1g, all of that over m2 plus m1. Now let's just check, right, before we put in our values. Let's check, does this have the right units? So I want units of acceleration on this side and that side. So g has units of acceleration. And in fact, I could factor out the g right here. So this is kilograms times acceleration minus kilograms times acceleration. So the whole top up here has kilograms times acceleration. The coefficient doesn't have units. Down here I have kilograms. So I have kilograms acceleration divided by kilograms. That gives me units of acceleration, so that's good. Okay, let's just plug in our values. So I have A is m2, which is 2 times 9.8 minus 0.3 times 3 times 9.8. Is that right? Yeah. All of that over m1 plus m2, which is 2 and 3, so it's 5. Okay, let's put that in the calculator. Drop. Oh, it's on. Drop. Drop, drop, drop. Okay, 2, 9.8 times 0.3, 3 times 9.8 times minus, divided by 5. I get 2.15 meters per second squared. Let's just do a couple other checks here. What if the coefficient of friction is 0? That term goes away. In that case, this would be the same equation for a half Atwood machine. So this would be the force that accelerates the whole thing, m2, but then m1 plus m2 accelerates. So that is correct. And then we could also check what if, now there is something here, right? If friction is too high, if this is too high, then this term could be greater than that, and that would make this whole acceleration negative. So that means that the acceleration of this would be negative. It'd actually be accelerating that way, but moving that way. Is that possible? Yes. What if I had very high friction, I push it, it would move and slow down, and it would stop. So it would be moving that way, accelerating that way. Okay, and this would be accelerating up because we said the acceleration was down, but we got a negative value, so it'd actually be accelerating up. Although moving down, I know that's tough, but that could indeed happen. Okay, that's that problem. Let's do another one. The end.